Alright folks, so welcome to AP Physics 1 practice exam. Now, I'm sure you don't see my face, but the key point here is just to simulate the real conditions of the real exam, which is occurring tomorrow. Thank you. Now, all I'm going to be doing is taking the paper, and of course you can see all my scrapbook as I gather up.
Maybe you should have used a marker instead of pencil.
Okay, so we're gonna go ahead and begin shortly, but in the meantime, you folks out there can go ahead and comment any topics you want me to discuss separately. In the meantime, as we gather our materials, you may want to grab some pencil and paper in case you want to follow along with me as I solve these problems. Okay, so go ahead, I'll give you a few minutes, and we shall reconvene in a few seconds. Okay, of course, to those of you who are not aware, tomorrow is the AP Physics 1 exam, and it is often called the hardest AP exam of all 30 APs. So before we go ahead and get started, let me introduce you to the book I'll be using to take this practice exam. This is going to be the AP Physics 1 book, and yeah, we're gonna go ahead and take the first practice test using traditional pen and paper. Okay, so I've got both my paper ready, I've got my whiteboard ready, so let's go ahead. Why don't we get started? So, and of course any scrapwork necessary can be done on these boards. Okay, so why don't we get started with the AP Physics exam? Okay. And of course, this year, apparently you do not need the calculator, but it's always useful to have one by the side, just in case. So, I've not seen these questions before, and I'll have practice for this prior to this simulation. So why don't we begin fresh with the first practice test on page 7. So, practice test 1, I've got my pen and paper ready, so why don't we go ahead and begin. And of course, why this helps you is because you can see how a real test taker thinks about the problems as I try to solve them. Okay, sometimes I'm going to skip them for the sake of time, sometimes I'll fully solve them just for the sake of elaboration. So why don't we go ahead and begin. So, if a ball is rolling down an inclined plane without slipping, which force is responsible for causing its rotation? Okay, so let's sketch this idea out. We've got a ball rolling down an inclined plane. Okay, so hopefully you all see this. Yes, okay. So there we go, that's much better. So I've got my ball and my plane. And my ball is rolling down my inclined plane with angle theta. Now, what do I want to know? If the ball is rolling down an inclined plane without slipping, which force is responsible for causing its rotation? Well, what do we mean when we say causing its rotation? Well, rotation is really happening when the ball experiences angular acceleration. And when does an object experience angular acceleration? When there's a torque exerted upon the object. Now, How can this torque occur? Well, torque is the rotational analog of force. Okay, so what are the various things that can exert this torque, causing the rotation of the ball? Well, there's friction along the tracks. That's one possibility, right? So friction is one possibility. Is gravity a possibility? Well, as a matter of fact, no, because gravity only acts directly downwards on the ball. Okay, so gravity is out of the question because gravity acts perpendicular, or sorry, it acts just straight downwards on the ball. Unlike any force that can exert a torque on the ball, causing it to angularly accelerate. How about normal force? Can normal force be a possible force that is causing this rotation? Well, once again, our answer says no. And why is that? Seems like we've got problems displaying the whole screen. So why don't I move this a tad bit, and there we go. Our problem should thus be resolved. Let's see how much of the screen we can really cover here. And just about that much. That's great. Okay, so why don't we put some markers in there to indicate that. But in the meantime, I want you to consider whether normal force can or cannot exert a torque on the ball. Now remember, the ball is moving parallel to the inclined plane, so you have to think about which way normal force acts, or which direction this normal force acts upon the ball. Okay? Now, as you do that, I also want you to consider why friction is a plausible means of exerting torque on our ball. Okay, so in the interim period, I've recovered some tape and such to mark where our line ends. So we've got it right about here and right about here. Okay. Okay. So let us continue solving this problem. So it seems in the likely scenario that normal force cannot be a force which can exert a torque on our ball here. On the other hand, friction can, because friction does act in the direction that the ball is moving. So the question is it static or kinetic friction? Kinetic friction that is causing the ball to rotate. Well, think about this. The ball is already rolling down the incline, so of course it's going to be kinetic friction, at least that I believe. So why don't we go ahead and circle that answer on our key right here. Oh, whoops, meant kinetic. So now let us proceed. Okay, so question 2 asks us, the graph above shows the velocity of an object as a function of time. What is the net displacement of the object over the time shown? Well, this is a standard graph question, right? And really the best way to approach this is look carefully at the graph and consider the units of both axes. So let's do that. Let me just adjust camera, and there we go. Okay, so how can we approach this question? Okay, so to answer this question, let's try to reread it one more time. The graph above shows the velocity of an object over a function of time. What is the net displacement over the time period shown? So displacement, of course, recall, is the area under the velocity curve. So why don't we sketch this out in our little whiteboard here? So what do we have? What does our graph look like? Well, we have something like this, right? So we have kind of trapezoids, and then boom. So let's put in all the tick marks to indicate where this begins and ends. I've got 4 right here, and I've got 3 straight down the vertical. Of course, this is also 3. This is V. This is T. We're looking for the area under, which is going to be displacement. This is 9, and this is -4. Okay, -4. So what is the area over here? Well, just so think. This is 4. This is going to be what? 3. So 7 over 2 times 3. So that will give us a cool 21 over 2, or 10.5. And how about here? Well, once again, we have another trapezoid. But this time we also have a rectangle, if you will, underneath our trapezoid. And this rectangle is going to add a bit to our area, because, as you can see, we do not fully reach back to the x-axis. So, let's see what that is. So I'll have 2 trapezoids, as a matter of fact. So the first trapezoid is going to have an area of, this is -2, so it'll certainly have a height of -2, but what about the average of the bases? Well, I'll have 5 for one, and for the other it seems like I'll have 4. So 4 and 5 make 9, and then add on -2, so -18 over 2 gives us -9 for that. Although it's of course a good idea to make sure. As a matter of fact, why don't I think it's better if I just approach this via paper and pen rather than my standard whiteboard. So let's take a look at this on the graph paper. Okay, so I've got, what have I got? Well, of course, I know that this is 4 and 3 make 7. Average those to get 7 over 2 times 3, which is going to give me 21 over 2. So let's see. Let's continue on, shall we? So this is going to be quite a tricky problem, not because it's hard, but because it's just numerically full of loopholes. So I've got what, 4 by 1, that'll give me a -2 of a triangle right there, and I've got a what, 4 by 2 giving me a -8 right here, so -10 in sum. And then I finally got another trapezoid, as a matter of fact. And this trapezoid goes from 5 to 9, so that's 4. Another 5 to 9, or rather 5 to 8, so that's 3. So keep that in mind, 7 over 2, and multiply that by the difference in height. 7 over 2 times 2, okay? So that's great, that cancels out. So I've got what? In sum, I've got 10.5, -8, -7, -2. So that'll give me none other than, so let's calculate this out. -8, -7, -2, and you can see a cool -6.5. Okay, so why don't we circle that answer, and we are good to go for number 3. An object is resting on a platform that rotates at a constant speed. At first, it is a distance of half the platform's radius from the center. If the object is moved to the edge of the platform, what happens to the centripetal force that it experiences? Assume that the platform continues rotating at the same speed. Okay, so this is a great question that really focuses on unit 8, which is unit 7, sorry, which is rotational motion or kinematics. So let's take a look. Let's hash this diagram out. So I've got a half r from this dot to whatever square is lying on, and of course we're looking at this from the top, and this is the full radius. Okay, so great. So this is our object of interest, this little box. At first it's rotating from half r, then from full r. Okay, so what happens to the centripetal force that the object experiences? So what is centripetal force? Well, that's a hard question to answer, but as far as I recall, centripetal force is mv squared over r. So does that help us in any way? Well, let's see, what does it ask us? What happens to the centripetal force the object experiences? Well, let's see. Our radius changes from half r to what, r. So assuming that the numerator stays constant, would our centripetal force increase or decrease? Right. So which one is bigger here? Well, having a lower numerator increases the fraction, meaning that over here the centripetal force is greater than over here. So from my standpoint, I would say that the centripetal force would be greater right here than after we moved it. How much greater? Well, it seems to be a linear proportion, so it seems to be 2 times greater, because half on the denominator is going to give us 2 mv squared over r as compared to mv squared over r. This one is clearly twice as big as this one. So why don't we go ahead and circle B for that. Alright, so that was, we made some interesting headway. Why don't we keep making progress? Number 4. Now, before I begin number 4, let me first read it and ask you to consider what the correct answer may be. After a few seconds, I'll return and enable you to see if your answer is correct. So, a car of mass 1,000 kilograms is traveling at a speed of 5 meters per second. The driver applies the brakes, generating a constant friction force, and skids for a distance of 20 meters before coming to a complete stop. Given this information, what is the coefficient of friction between the car's tires and the ground? Now, this is a standard kinematics question, and I ask you to pause and ponder before we continue. Good luck. Alright, folks. So let's go ahead and examine this question. Hopefully that was enough time for you to pause and ponder. Okay, so let's take a look. I've got my car going at 5 meters per second, and apparently it applies some brakes, 20 meters, right here. So at this point the car applies brakes, and at this point the car stops. So VI is 5 meters per second, VF is 0 meters per second. Okay? Hopefully that's clear. And in the case that it isn't, why don't I make it even better? Okay, so that's great. VI to VF, we have a distance 20 meters. We're also given a mass of 1,000 kilograms. Any other relevant information? Okay, so there's constant force of friction. So free body diagram would be helpful. So why don't we draw that right now? So here's our car. It's got so initially from here to here the car is traveling, and from here to here the car is traveling, and here's where the car stops. So here VF is 0 meters per second. Here VI is 5 meters per second. We know our car's mass is 1,000 kilograms. What else? Distance from here to here between application of brakes and the actual braking of the car is 20 meters. Seems like that's about it. Of course, from here on, the car experiences a net force exerted by the brakes. Okay, so much like that. So I advise you to analyze this free body diagram and see what you can come up with. Alright folks, so thank you and we'll see you next time.